In the first part of this video on generics, we will explain the reason generic syntax was added to Java, describe its syntax when applied to classes, and provide an example of a generic class and a client class that makes use of it. Another term that is sometimes used to describe generics is parameterized types. Generic code makes it possible to write code in which types are defined by parameters that are subsequently instantiated with actual types once the code is used. We begin with an explanation of the benefit of the syntax that was added to Java to support generics. It was possible to write generic code in Java before explicit generic syntax was added to Java in version 5.0. Before that syntax was included, generic classes were defined by defining collections whose components were of the object class. The fact that all object names are references made this approach possible, because all references occupy the same amount of memory, regardless of how much memory the objects that they refer to require. The purpose of the generic syntax is to allow the programmer to constrain the type of the elements that can be in the collection at the point of instantiation. Without the generic syntax, it was necessary to downcast objects that were removed from a generic collection. Because downcasts are potentially unsafe, such a requirement was undesirable. When generic code is defined using explicit generic syntax, such downcasts are no longer required. First, we consider an example of how generic classes were implemented prior to the inclusion of the generic syntax. The example that we will use is an implementation of a stack. Although Java contains a predefined stack class, understanding the implementation of a stack is beneficial, and because it is relatively simple to implement, it makes a good example. Notice that the object stack class is a generic class implemented by creating an array with elements of type object. In addition to the array itself, it is necessary to maintain a subscript that indicates the position of the top of the stack. By initializing top to 0, it actually contains the position where the next element will be pushed. In addition, it contains the number of elements currently on the stack. So by initializing it to 0, we are initially defining an empty stack. The push operation allows objects to be added to the stack. Notice that the type of its parameter is object. This statement adds the parameter item to the stack and also increments top. In this case, it is essential that the increment operator be a postfix operator so that the incrementation occurs after the assignment. For simplicity, no check is made to prevent a subscript out of bounds should the stack overflow. The pop operation returns the top element of the stack. Its return type is also object, as it must be. This statement removes the top element by decrementing top and returns it. The decrement operator must be a prefix operator so that it occurs first before the element is returned. As before, for simplicity, no check is made to prevent a subscript out of bounds should the stack be empty before the call. We have also included a method to check whether the stack is empty so clients can prevent the possibility of a stack underflow. As mentioned when we described the initialization of top, top being 0 signifies that the stack is empty. Let's examine a client class that makes use of our stack class. The main method of this class reads in a file of integers and pushes them onto a stack and then continually pops the stack to output them in reverse order. An explicit stack is needed to solve this problem iteratively. Recall that when solved recursively, the compiler's runtime stack could effectively be used, which greatly simplified the code. The first step is to open the file that contains the list of integers to be reversed. Next, we define the stack that will be used It is an instance of our object stack class. Each time an integer is read in from the file, it is pushed onto the stack. Now let's scroll down to the second loop. When the pop method is called in the main method of the reverse integers class, the object at the top of the stack is removed and returned. Notice that the object that is returned must be downcast to B-type integer. Next, let's run the program. Now, let's examine the input file. Notice that the output does indeed contain what is in the input file, but in reverse order. Next, we introduce the syntax of generics that was included in version 5 of Java, beginning with how to declare generic classes. When we declare a generic class, we must include a generic type parameter. This type parameter can be thought of as a placeholder for an actual type name. Here is the syntax of the class header for a generic class. Notice that what follows the class name is the generic type parameter that is enclosed in corner brackets. Recall that Java has a widely observed set of lexical conventions. Constant names are all uppercase. Variable and method names are all lowercase with the exception of the first letter of subsequent words, and so on. The lexical convention for a generic type parameter is a single uppercase letter. Here is an example of a generic class header. It is similar to the one we will use in our next example. Notice that after the class name stack, an uppercase T is enclosed in corner brackets. T is the generic type parameter. Next, we examine a revised version of the stack class we examined previously, but this time it will be written using the generic syntax that we just introduced. Here is the class header that includes the generic type parameter T, which is enclosed in corner brackets. In the previous version, the type of the array stack was object. Now its type is T instead. Nonetheless, when the array is instantiated, it still must be of type object, and then be typecast to the generic type T. The parameter passed to the push method is now T rather than object, and the return type of pop is now T instead of object. To use a generic class, it must be instantiated. Next, we consider the syntax required for such instantiation. To instantiate a generic class, we must supply a generic type argument. Let's consider the specific syntax that is required. The syntax for generic class instantiation is similar to what is used when a generic class is declared. After the class name, the generic type argument, which is an actual type name, is placed in corner brackets. The actual type then replaces all occurrences of the generic type parameter in the class definition. Now, let's look at an example of a declaration that contains an instantiation of a generic class. Assuming stack is the generic class that we illustrated previously, the object S will be an instance of the stack class constrained to contain only objects of type integer. When generic syntax was first added in version 5, it was necessary to include the generic type argument in the call to the constructor. In version 7, that requirement was dropped. The compiler can infer that type. Next, we revisit the program that we discussed earlier that reads in a file of integers and displays them in reverse order. Unlike the first version, this version uses the class generic stack, which we just examined. This declaration contains an instantiation of the generic stack class, constrained to contain only objects of the wrapper class integer. Notice that by using such a class, the downcast is no longer required when calling the pop method. We will forego running this version because it behaves the same as the previous one.